Welcome to my presentation on experimental demonstration of multimode optoelectronic oscillator at 2.4 GHz. I am Siva Subramaniam, a master research scholar of Indian Institute of Technology, Madras. There is a growing demand for ultra-low phase noise RF oscillators in several applications such as radar, clock recovery, and RF signal detection. These RF oscillators are based on frequency multiplication of a low frequency source, due to which phase noise deteriorates as 20 log n. An optoelectronic oscillator overcomes this limitation through its high Q factor cavity. In an OEO, the phase noise is independent of the oscillation frequency as well. The maximum achievable frequency of the OEO is decided by the bandwidth of the optical and electrical device in the cavity. The experimental setup of our OEO is shown here. Light from a narrow line with laser source is fed into a Mach-Zehnder modulator and travels via a polarization maintaining optical fiber and incident on a photodetector, which converts the optical signal into an electrical signal, which is further amplified, filtered, and sent back to the RF port of the Mach-Zehnder modulator via RF splitter. And the other arm of the RF splitter is connected to measuring devices such as electrical spectrum analyzer or a sampled oscilloscope. The RF power driving the MZM was varied from 6 dBm to 11 dBm for different fiber lengths in this experiment, and parallelly the phase noise measurement and time domain traces were captured. Since the RF bandpass filter's 3 dB bandwidth is greater than the cavity FSR, this OEO operates in multimode state. The left plot shows the phase noise measured as a function of different fiber delay lengths for RF power of 10.17 dBm, and the right plot shows the time domain results measured for different fiber delay lengths for RF power of 10.17 dBm. As you can see in the left plot, the phase noise has more is better at 19.98 meters compared to other fiber delay length. And in the time domain plot, you can see some distortion, which is due to short-term cavity instability. In this experiment, we have achieved an RMS jitter of 12.19 picosecond, meaning a 2.9% timing jitter. This plot shows a comparison of our OEO with the commercial RF source at 2.4 GHz. As you can see, our OEO performance degraded at low frequency offset compared to commercial RF source due to environmentally induced thermomechanical, thermoconductive, and double relay backscatter noise in the fiber. In conclusion, we have experimentally demonstrated a multimode optoelectronic oscillator at 2.4 GHz with a phase noise of -104.6 dBc per Hz at 100 kHz offset and an RMS jitter of 12.19 picosecond. Further phase noise improvement is possible by using a longer delay fiber with RF splitter having 3 dB bandwidth smaller than the cavity FSR, or adopting a dual loop OEO structure or use of a high Q cavities and micro ring resonator.